We're going to look at quality control done the AFNI way. So let's get started with this. So what do we mean by quality control? So we're not just finding ways to exclude data. We want to look at what's good, what's bad, what's uncertain. We also want to look to see how consistent our data is across all of our subjects. We will take into account the processing steps that we do with these data. And we want to know, is it suitable for our particular study? Like, is the region that we want to see, that we're going to analyze, is it in our field of view? So from our Frontiers paper, it says this is how we described it. It says quality control is the larger procedure of being as sure as possible about the contents of the data collection, from acquisition properties to artifact checking to regression evaluation. So we want to look at it in the whole pipeline, not just good or bad, but the whole pipeline of our analysis from the time we collect the data to our interpretations. So we divide up quality control into these stages. We'll go through these one at a time. The first stage is getting to know your data. And this helps us find the basics of our data sets. The orientation, the data type, voxel sizes, minimum, maximum, and so on. And we have these tools, the 3D Info, Nifty tool, 3D Brickstat, to help us get this information. We also provide example scripts that, like with our Frontiers project, we have example scripts for those to take a look at these kinds of facts from our data. So let's see what kind of facts we can get out of this. So for example, we have 3D Info, and it can show us the information about voxel sizes. So we can and number of voxels in each direction. So here we can see that this set of data, which was one of the Frontiers groups, had different matrix sizes, so different number of slices, different number of rows and columns in every direction, and the voxel sizes were very different. Sometimes they're very close to each other. We'll count that as pretty much the same, but these were very different from each other. And why is that? And that's going to have a very big effect on our processing and how we can look at this data. There's lots of different parameters, obliquity angles, TRs. Anywhere that it's different from across your subjects, that may mean that you'll have to process those subjects differently or exclude them completely. Another great tool is the Nifty tool. This lets us look at Nifty datasets particularly, and so we can take a look at these Nifty datasets and see things like the S form code and the Q form code that tell us the matrix, what kind of space the dataset is in, native or MNI or Talarak or other, or we can use it to find out what kind of data is the data stored in. So here, for example, we see that the data types are listed as code 16 and code 4, and that shows us that these within the same data set, some were saved as float and some were saved as signed short 16-bit integers. This may have an effect on how we have to process our data. The floating point will take twice the amount of space as the 16-bit data. That's one small example of how these things at the beginning are very important. And when we look at data in the AFNI group, this is the first thing we do, is we start with 3D Info and Nifty tool, and we want to see, what is this data that we've got here? Is the orientation set right? Is the orientation different from one subject to another? All very important characteristics of our data. Another tool that we need to talk about is AFNI-Proc. AFNI-Proc, or .py, is our pipeline for fMRI processing, and it will collect a lot of information for us We get to choose which processing blocks go into it. It's pretty simple to use, although it has hundreds of options, so you can use it in many, many, many different ways. It can you'll have to think about the ways that you want to use it, but what comes with AFNIPROC is these automatic quantitative summaries and HTML reports that we need for quality control. It generates these reports, and we can take the output from every single subject's report and combine them across subjects with this tool called GenSSReviewTable.py. And we can have it look for outliers. For example, like here, we can say, what version of AFNI did we use to process the data? If it's different for one subject from another, will that have an effect on our data? Generally, you want to use one version of AFNI, not at 5 different ones. So you want to reprocess your data with a consistent version. You also want to have, final voxel resolution should all be the same. The number of TRs per run will generally be consistent across subjects. And you'll want to know these kinds of things. Okay. Let's continue on to the next step of this. The AP Quant, the quantitative review of our data. So here we're going to use similar kinds of tools, and we're going to look at things like motion and censoring and global correlation and TSNR, and we do that again with the tool GenSSReviewTable.py. So let's look at an example. Now here we're going to report outliers based on some threshold that we get to set. So the degrees of freedom. What fraction of the degrees of freedom that we started with do we want, that can we end up with? If it's less than 60%, we'll say that we'll reject this particular subject. If we've censored data because of motion, because of outliers, if it's greater than 0.2, 20% of the data, we can say we will reject it for that. And we'll have motion limits, average motion, maximum motion, global correlation, the amount of correlation among all voxels in the brain. How correlated is every voxel with every other voxel? If it's more than 0.2, that means the brain is pretty much all correlated, and it's going to be difficult to pull more data out of it. We'll also be looking at whether the data is flipped, left-right flipping. This is a very, very important problem that we find with lots and lots of public data sets, and it probably happens in private data sets too. So these generate tables. This is an example of a table. And so here we have the degrees of freedom, and we rejected for this group of 20 subjects, we've rejected 3 of them just because of the degrees of freedom that are left over. We rejected 4 subjects because of the censor. We've censored too much data. In one case, we censored more than 60% of the data. And we found that 2 of these subjects were left-right flipped. We'll show that a little bit more in the next part of the talk here. Okay, so that AP Quant showed us all these automatic tests. So we can just decide ahead of time on the limits how much motion, correlation, censoring. It's easy. So we don't even have to look at our data. Or do we? Well, the answer is we do have to look at our data, which brings us to the qualitative review. Okay, so AP Qual is the slightly squishier form of quality control. We're going to have to look at our data and decide, is this reasonable? Is this reasonable data? And For our example, in our Frontiers project, we looked at the quantitative results. We used those to reject about half of the data that ended up being finally rejected, and the other half was rejected based on qualitative review and in-depth GUI investigation. Okay, so what kinds of tools do we have for qualitative review? We have AFNIPROC, which generates HTML pages for us, and we can open those HTML pages with AFNI Open, and on each of the index HTML pages that it generates for every single subject, or we can use this new tool, openapqc.py. And it's fairly simple to use. The interface is a single command line, and here's an example that you give it the files for every subject. You give it the index file, so this is going across all the subjects for one particular site, and saying open up every one of them in a different tab in Firefox or Chrome or Safari, whatever is your default browser. It will open them up and show them on multiple tabs, and you'll see the report for each of them. And we can have that even jump to the anchor reference hash for a particular part of the QC report. All right, so now we're in a terminal, and we can look at the output for AFNIPROC's QC. And when it ends, it shows you something like this, and you can use AFNI Open to open the index file, or you can use this new OpenAPQC. And so it just takes one or more index.html files, and I'm just going to copy and paste that. Okay, so now that is opened, here's Firefox that started over here, and so this is what the QC pages look like. Here we have at the top, we'll start at the top and work our way down. We have the name of our hash references. These are the different parts of our QC page. So VORIG, VE to A, we'll go through what these all mean. Our subject is over there. And we'll talk about these too. Okay, so let's say I look at my VORIG section here, and I can go down to it by hitting that. Each of these takes you to that hash, the hash reference. So you can go down to VORIG, and so here we have the API data in the original space. So this is useful. We can see if there are any odd artifacts in there. We can look at our anatomical in its original space. This has been skull stripped, obviously, because AFNIPROC sees the skull strip version as its input. But we can go over here and say, is this good or bad? And say, okay, this looks it looks good to me. So let's say I'll put a plus there. But if I didn't like it, I could put an X, and if I weren't so sure about it, I could put a question mark. And so if I do Control or Command click on a Mac, so this is a Mac, so I'll do Command, I can enter a comment about that and say, all looks good here. And keep that and close it. Okay, so and as I go through it, I can mark the plus and the X and the question mark for each one, or I can mark them all. And you can mark all the ones that you haven't marked by clicking one of these guys once. If you double click it, it will switch them all to that setting. So I can do all X, all bad, or I can clear all of them too. And so that's the general interface. You would put some final grade here. So is it a good subject, or you want to keep the subject, or you want to exclude it, or do you want to look at it some more? Okay, so let's go through some of these, some of the sections in here. You'll see right away Compared to the traditional opening of this in the past, these now have these AV and NV buttons on the side. We'll see a couple other buttons as we go down. So let's go to something maybe a little bit more colorful. We'll see here, here's some original alignment. Here's the EPI to anatomical alignment. Here's the template to the subject to the template alignment. So the anatomical to template, did that aligned into a standard space. And get down here. Here we've started to see some things about our model for this. So this is in the VStat section, and we have the full FStat. We may have some of the beta coefficients here, so we can look at that. So this might be useful to see here. So let's run that. We have the AFNI view and the NIFTY view. Let's run the NIFTY view first. This is the knee view, knee view. And this is a new part of this interface, and it opens up this small viewer at the bottom here, and in this we can scroll through the slices. It's an interactive viewer, so we're not limited to this fixed set of slices. We can see all the slices, and it's been set up to look something like the way AFNI looks too. But it does have this additional 3D rendering in here, and you can type C on there and scroll, and it will clip the planes. You can see that, and so that's another cool way to look at your data here. So if you click the NV again, it will close the knee view instance, and you can run something like the AFNI viewer here, and then this instead starts AFNI, and so then you have all the functionality of AFNI. This shows all the same kinds of montages that we're seeing in the web page, but now these are all interactive, right? I can click around. I can turn off the montages. That kind of thing. So again, we won't talk about all the functionality of AFNI because that would be way too long. But there's a way to look at our data in much more detail. So we can go from this quick view from the HTML into a deeper dive into the GUI in AFNI fairly easily at the places where we might have questions. Okay, so over here, this pop-up tells us when we're done, we can close it through here. We can close the AFNI GUI here, and it brings us back to the web page. Okay, and then we have other things. We have the IC button and the GV button. The GV button is for graph viewing, and the IC is for Instacore. So let's see, is there's something. Okay, so yeah, we have these data sets don't have too much wrong with them, but we can take a look at this with a couple of these things. So let's just for fun, let's start Instacore here, and this. We'll start Instacore inside AFNI. Takes a few seconds to do all the correlations, and so now we have instant correlation. So if you're not familiar with this, this calculates the correlation of every voxel with every voxel in the data set with every other voxel in the data set, and I just have to select the seed. There's certain settings I can do in the setup iCore button here, but this has chosen some things for me. Those are specified here. They're what we think is appropriate based on the data set, the part of the QC that we're launching it from. So I can if I do Control Shift left click, that shows me correlation with that voxel. And I can drag this around by holding the Control Shift down and moving the cursor, and it shows me what's correlated. So this is kind of endlessly fascinating, but it's also really useful for quality control. We found that for these 169 data sets that this was one of the most important ways to find problems. We can find problems with coils, we can find problems with motion, we can find lots of different kinds of issues that would be more difficult to see without this instacore correlation. So really, really good tool that's not available in other packages. All right, so wanted to make sure you've seen that. Let's see. Can look at the graph view button. This is something similar, and here it's loading our error time series, and we can look at patterns in that. This is mostly a pretty good data set, so it's not too much to talk about, but you can look through the data for data sets that have problems. They will sometimes be very obvious in the graphs, especially. Like the graphs will fall down, the graphs will plateau. So it's another good tool. Okay, so I'm going to close that. Go down to motion. Okay, motion, we see our typical motion plots. We've got plots of the E norm. These are the Euclidean norms of the differences between time points, and we can see that we have a couple big spikes. These end up getting censored based on our motion limits for E norm, and these are the actual motion regressors, or the motion amounts for the six, the affine, the rigid body motion that we use for motion correction. And these motion parameters: the pitch, the roll, yaw, and the three translations. We also have the gray plot. This is one that a lot of packages seem to like. We probably don't use it as much ourselves, but the idea is that large motion will generally show up as deeper vertical stripes. This sometimes does happen, and I can also find outliers with that. Down here we're looking at regressors, and so the regressors in our task model, do they match with when we're censoring data? Does motion match the regressor, the censoring? So if we have task-related motion, we will want to address that soon. Sooner is better than later, and try to take care of that. So if we have a task that's very motion related, like signing or singing or something like that, or finger tapping, if we see that the motion is related to it, it'll be more obvious here. We get the degrees of freedom that we use. I'm going to jump down to the radio correlation, and so radio correlation, and I'm going to go back up a little bit. Sorry about that. The core brain. So core brain, this is the average amount of correlation every voxel has with the global signal average. And so it turns out that this is a good way for looking for large problems. So if we see that every voxel in the brain is showing correlation, it's going to be difficult to disentangle everything else out from it. So we'll use that as a marker that motion is still in the data set, and it's in most of the data set. So in this case, this is good. This is a good sample, but I'll show you in a moment some bad examples. And let's see, what else can we talk about here? So, oh yeah, the radial correlation. Another surprisingly effective way to find problems. So radial correlation, this shows us what is correlated in a 20 millimeter sphere at around every voxel. And so this has been very important in showing us problems in coils. And then we can take the radial correlation output, radial correlation, and go to Instacore and look for the problems in the original data and look at this time series and see, are there indeed problems? And this was very important for looking at stripes, at spikes going through data, at bad coils, a number of problems. So radial correlation, definitely should put that in your AFNI-Proc processing. And finally, this one that's lit up in pink here, it says warns. It's mild in pink. If it's in red, you have strong warnings. So you should go and look to see what kind of warnings there are. This is all, pretty good. There's only one mild correlation between two of the regressors, but the rest is okay. This also checks for flipping. We can see that the flipping is an important problem that we see again and again. The left-right flipping. So here is the original data set, and we just tested against the left-right flipped. Does it align better with the anatomical data set? Does the EPI, when we flip it, does it align better? And if it does, that tells us that the data is probably backwards. Another thing that we discovered when we were doing this analysis for Frontiers, that several of the sites had these kinds of problems, these high variance lines. This has it too, but not as bad as some of the sites. And these are more or less difficult to find, and sometimes there's so many of them they really can dominate the signal through much of the brain, and so if the SNR will be very low in those along these lines, and so this is a great way to see them, and you'll want to go and look at these particular locations in AFNI. And finally, there's a summary at the end of this to show you something about this particular subject, all the statistics about it. These are the same things that we can get in the review table, but just for this one particular subject. Okay, so let's now look at some examples from the Frontiers data of problems. So we saw lots of different kinds of problems. Let's see what they look like in the same kind of index HTML pages that we just looked at. So here we have some examples. We've got a dropout region here. You can see that in the front too, and the sides. You can see over here, so that was fairly minor, maybe not enough to affect the what you might be studying, but you'll have to consider whether that's the case for your data. Are you interested in something in this part of the brain? If you are, then you'll have to exclude this particular subject because there's a big dropout there. Here we decided this was rejected because of these kinds of these distortion artifacts. We had ghosting, front and back, this kind of aliasing. So this was rejected. Here we see a fairly common artifact, this ringing artifact, and there was also distortion that you see very often like this in the anterior parts of the brain. and you'll see stretching in the posterior parts. So this one, we mark this as uncertain. This yellow means uncertain here. Here, this subject had extra large ventricles, and we said that's uncertain. This is likely not to align too well to a template because of the difference is so large. So that's one reason to exclude it. There may be other problems that come along with that too. Down here, I think this one is fairly obvious why we rejected it. It was upside down. So sometimes we get these kind of surprisingly obvious problems. Here, so if you're doing resting state, you will have a different set of pages, HTML results. You'll have some information about seed-based correlation instead. And so here, for resting state data, we'll have the seeds shown for default mode network, for the visual network, and a couple others. Okay, so here's what a normal one looks like for the default mode network. And here's what we saw for some of the subjects. Here we saw this very high correlation in the mostly superior part of the brain, and because it was so large, we decided to reject this particular subject. So this subject was excluded. And now over here we have a lot of, this one was pretty noisy compared to this, but we said, okay, we're not sure about it. We could go use Instacore to go look more in this, but in the end, we decided that it was probably okay, and we kept it. Here's very low correlation. So you can have very high correlation, you can have very low correlations. Here, almost nothing seemed to be correlated. That might be a sign that the subject is asleep. So there are considerations of all these different things. Similarly, we have these kinds of things in the visual network, and we had a lot of subjects here that in the 200 group that had large correlations in the middle of the brain that didn't make any sense. They're not physiological. Okay. All right. So I'm going to continue on. Okay. So I did mention that the core brain. So this is the correlation of every voxel with the global signal average across the whole brain. So this is up at the top. This is what a normal subject would usually look like, and you can see here everything is correlated. So that's difficult to use at that point. So we rejected that. These are also too highly correlated. So we rejected these particular subjects from these particular groups. Okay, as I said before, we talked about RAD-core, and this is this radial correlation. We want to look to see how correlated data is with surrounding voxels, a 20 millimeter sphere around every voxel. And normally we would see things like this, but occasionally we see something like this, and it's usually a sign that there's a coil artifact. There's just too much correlation in one part of the brain. It's usually a large chunk. So a useful tool there for radio correlation. Now we're going to look at the TSNR. That's the temporal signal to noise ratio. That's classically used for looking at FMRI time series for quality control. And but this one, let's define what TSNR is here. So this is on the regressed time series. It's not on acquisition. It's not opposed to volume registration. This is after it's been regressed. All of them, the motion should have been corrected as well as possible. The modeling is included here, so it's the mean of the signal that goes into 3D deconvolve for our linear model, divided by the noise which comes from the error time series, the standard deviation of the error time series. So so that's how it's computed, and so we get TSNR maps out of this, and we can look to see what a good one is here. That's up here. So this is generally fairly high through the brain, more or less consistent. Comparing that to this one, you can see, and I've blown up a area one of these slices to show you that this has a dropout. Now, very often there are lots of researchers who are interested in these parts of the brain, and if you are interested in this part of the brain, and the thalamus, and the nucleus accumbens, and that kind of thing, you will be disappointed by your results probably, because the SNR is so low in this part. So you want to make sure that if you are interested in that part of the brain, that the SNR is high there. Okay, so let's go on to another interesting example. So in this subject, subject 403, we saw that this kind of thing happened. We'd get these stripes. And this kind of stripe made us a little suspicious, and we ended up going into the AFNI GUI to explore that more. We found that we had high correlations that were not explainable around these areas. It was very noisy. And every subject in the whole group had similar large artifacts, and these were extensive. So we ended up removing the whole group, excluding the whole group in the Frontiers data sets. Okay, so let's go on to another set. Those kinds of things often showed up as variance lines, and since we wrote that paper, we have a new tool that's now included as part of AFNI-Proc for looking at these variance lines, and it can find these lines that show up at certain frequencies. These are kind of like they're certain radio frequency interference, something like a zipper artifact that show up at particular locations in our axial slices, generally when we acquire them axially, so probably corresponding to a set of radio frequencies, and so we can get those coordinates here. As I told you before, we've had a long history of looking at left-right flipping, and we see this for this data set. This one looks okay, but then we go to this data set, and if we look at the original versus the flipped one, the flipped one aligns better. We measure that by the cost function of the alignment, and so we know that the flipped value is a better cost function, and we can visually see that here. So we have a number of subjects that were flipped in all these data sets, and we find this continually. Okay, so we've talked about that the AP qual part. We've touched on some of the GUI parts too. So from the HTML pages, we can open up AFNI or NeView. We can also open up AFNI, the AFNI GUI, the Summa GUI, and Instacore inside the AFNI GUI as we want to go deeper exploration. So for those data sets that we've marked as uncertain, we can go and look at them in more detail with the GUI. And so that's what we recommend doing, is looking at data sets as deeply as you can to see if they have any artifacts. Okay, so here's some examples from using Instacore on some of these subjects. So here we have the seed-based correlation for some resting state subjects. These all look, fairly okay. Well, the seed-based, we've done Instacore on something, some random spots. We click around, and here we click and we find these kinds of artifacts. So extensive correlation in parts that aren't physiological. And this was the 400 series subjects that I just talked about with those lines. You can see these kinds of artifacts would show up. We also have the 200 series of subjects, the site 2, and this ended up also being excluded for the whole group, because all subjects ended up having these high correlations that weren't physiological. And you can see some of these kinds of effects. This is a particular subject this was not part of the Frontiers project, a different one, where we saw this high correlation just in the anterior part of the brain. You could see this with radio correlate, but you can also see this in these graphs. In this part of the brain, all of a sudden you have these big drops, and we think that's because of a defective coil that the wiring would intermittently disconnect. And this is a problem that we see from time to time. Okay, so stimulus data, task-oriented data, requires some special attention for the stimulus timing. That we want to look at the motion plots. We want to see if there's correlation with the stimulus in the stimulus correlation with motion, and are the stimuli correlated with each other, which is something we want to avoid. Okay, so did they respond to the task? So we want to see compliance also. And in the quality control HTML pages, we produce F-stats and T-stats and the model, the full model, the individual stimulus response too. Here, let's look at an example of a task quality control method. At the top of the screen, you'll see that we have these the F-stat model, and the F-stat is fairly low throughout the brain, and it was certainly different than most of the other subjects. But we also found that this subject had a lot of motion, and the motion ended up eliminating the subject, but we might want to explore why the subject was eliminated. We can look at these censored time points where the motion was too high. They've exceeded these motion limits, the E-norm limit, or they've exceeded the outlier limit, these cyan lines. And then look to see if they correlate with the tasks, the two stimulus classes, one called task 0 and the other called control 0. All right, so we have these two stimulus classes. It looks like there might be something going on, so we mark that as uncertain. We can also look at the sum of the regressors, all the regressors together here, and see if those two together are correlated with the motion. Okay, so that's one way that you can look at task data a little bit differently. Okay, here you can also just look at the motion plots in these two forms, one with the motion parameters, and the other, this is with the gray plot, or the carpet plot, some call it. Okay, so let's summarize what we've talked about. So in the real world, these data quality issues are often missed, and hopefully with the methods you've seen today, you'll be able to find them. But we've only covered some of the problems with fMRI data. There are many, many more, and ones that we've seen, and then there will be new problems that we haven't seen yet. And if you're using following our mantra of helping users stay close to the data, you will be a step ahead of that. And so use these kinds of QC steps to stay close to your own data. Finally, I want to acknowledge all my colleagues, Rick Reynolds, Paul Taylor, Bob Cox, Taylor Hanayak, and Chris Rorden, who contributed almost all the work for all this. Thank you very much.